Good morning, everybody. Welcome to the first invited speaker session of SC17. People in the back, there's lots of space in the front if you want to come forward. Of course, this was set up for the plenary speakers, and they haven't had a chance to trim it down yet. So our first talk, I have the honor of introducing someone who doesn't need an introduction to this community. Paul Messina has been a leader for 40 years. Most recently, he created the Exascale, or was the founding director of the Exascale computing initiative in the United States. And he's now at Argonne spinning up a computational sciences division. So he's going to tell us about exascale computing.
Thank you, Bob. Good morning. I'm here to tell you about the US Exascale project that I was very pleased to lead for 2 years, and is now being led very ably by Doug Cothe of Oak Ridge National Laboratory. So my talk is in 4 parts. First, I thought it'd be good to remind ourselves of why are we doing this in the first place. Then I will describe the project and the challenges that we've identified, at least some of them, and then early achievements. So the reason I think we're doing this is because we expect to be able to advance a lot of fields in many different areas. Scientific discovery, be able to do material simulation that's predictive of complex materials, including with impurities and dopants. The nuclear weapons stockpile needs to be curated, and simulation is a key part of that. 20 years ago, I played a role in the Accelerated Strategic Computing Initiative for that type of application. Combustion modeling. We all would like to have fewer emissions that are noxious, as well as getting better mileage. And a lot of that is done through combustion modeling. How about precision medicine for cancer? That would be great, and it relies on huge amounts of data, as well as simulations and machine learning and deep learning. Additive manufacturing of metals, and being able to qualify those devices that were constructed that way. We can't do that now, but that would help the economy. Earth system modeling, being able to do cloud resolving regional weather forecasts. Even accelerator design, well, certainly that's for scientific discovery, but part of the goal here is to be able to design and build accelerators that are much smaller, much cheaper, and can be used more affordably for medicine and for industrial purposes as well. Urban system science is a growing field. Those of you who attended the panel last night that Charlie Catlett and Pete Bettman put together got more information on this, but there are a lot of data sources, a lot of real-time issues, and they can help us make our cities better. Energy. This is the Department of Energy project, after all, but energy is important, and fusion is still being studied and very much dependent on computing, and small modular reactor for nuclear fission reactors is one of the projects that might help. In astrophysics, the SK array presentation that I think most of you may have seen gives you motivation for why we would want to do astrophysics. Another form of energy, one of the renewable ways, is wind energy. And so here you can see a wind farm, where the location of the individual wind turbines is crucial to getting very good efficiency, as well as the design of the blades. So on the right side there you see a wind turbine blade design simulation. And when you have these intermittent sources of power, such as solar and wind, then managing the electric energy, power distribution grid, which is a near real-time issue as well, turns out to be a pretty big exascale problem. So that's just a handful of them. I had to throw away many others that I had in the interest of time. And this slide is just a reminder that we've been looking at why it would be useful to have exascale for a long time. The first workshops were in 2007, and then in 2008 to 2010, we organized many other workshops, and the goal of them was in each area, like chemistry, high energy physics, nuclear physics, national security, what could be the payoff for Exascale. So do that first, and then eventually start the project. And so approximately 2 years ago, the project started, and I will be telling you about it, obviously. So it's part of the National Strategic Computing Initiative. Tomorrow afternoon at 5:15, there's a BOF on NSCI, so I would encourage you to see it. But National Strategic Computing Initiative also was put in place in July of 2015, so about 2 years ago. And its goal is to accelerate the benefits of HPC for the nation as a whole. The part that Department of Energy plays, it has a lead role along with DOD and National Science Foundation on the Exascale front. And within the Department of Energy, there are two parts, the National Nuclear Security Administration and the Office of Science, that are both funding and managing this project. This gives you a structural view of how we're organized. Applications, that's why I showed those images at the beginning, are of course crucial. And so application development is a big effort. Then there's hardware, and we're working with vendors and doing R&D to come up with better building blocks and better systems for Exascale. And in between, of course, is software that bridges it. So we have major efforts in applications development, in software technology development, and hardware R&D. And over in the right, in the yellow, of course, this is a project. And as you will see, it's a pretty big, complex project. And so we have a project office to help us keep track of what we're doing. At a high level, we want to foster application development through software and through better hardware design, make the systems easier to use than they otherwise might be, and to make sure that we don't get stuck in one way. At least two diverse architectures are part of our goal, and we hope to keep the US very competitive in HPC. Another way to put it, which is the way I often think of it, is we want to create an Exascale ecosystem. So you'll hear me say ecosystem and co-design a lot. Those are the two words I want you to take home when you think about Exascale computing project. So this ecosystem should enable the applications of the type we've been doing, but to be able to tackle things they can't do now. On the other hand, we want to enable new kinds of applications. The precision medicine for cancer would be one example of that. So not just today's applications, but also tomorrow's. And we want to make it possible to program these systems where, in many cases, with the existing programming models, but ones that have been adapted, enhanced, and tuned for the new architectures and the new application needs. And I'm hoping that we'll end up with an ecosystem that's suitable for people to use at a lower scale, much lower than Exascale, but then as their needs and ambitions grow, be able to move up. In the recent past, people working on small systems who then wanted to move to the biggest systems at the time often had to deal with a very different software stack, and I'm hoping we'll be able to mitigate that. There are 6 of the DOE national laboratories that we call the core laboratories for the project, and so they're heavily involved in it, but it's by no means the only places where the work is being carried out. We have 39 universities involved, 16 of the 17 DOE national labs, some additional federal agency laboratories. We have some companies. And because we also hope the ecosystem will be useful for industry and help US economic competitiveness, we have an industry council. And these are logos of the 18 companies that are currently in the industry council. It's an advisory council. It's made up mostly of end-user companies, the names that you would recognize: Eli Lilly, Westinghouse, Exxon. Some that you might not have thought would have Exascale interests: FedEx and Mars Candies. And also 3 software developers. These are commercial companies whose software is used by many industries. So we're hoping that they will help us guide our development in a way that's useful for industry. So the idea is to have accelerated delivery of an Exascale system that's capable. So capable, we're measuring by saying we want to be 50 times more powerful than what you can do on today's 20 petaflop systems. We're not using peak speed as a measure. And capable, wide range of applications. As you will see, we have quite a wide range, and an ecosystem for the reasons that I already mentioned. Now, okay, I thought I had killed everything so that wouldn't happen. All right, little break here. So this is a project, it's a 7-year project. It will end in 2023. So the place that the Exascale systems will be installed and the institutions that will buy them are the facilities that typically have the most powerful systems at any given time. So the facilities are the endpoint, and that means the project has to work very closely with the facilities. So the current plans are for delivery of the first Exascale system to be to Argonne National Laboratory in 2021, and then either that year or the next year, additional systems to Oak Ridge, Livermore, and of course later other facilities as well. This gives you a glimpse of that first Exascale system according to current plan. I say a glimpse because we can't say anything very detailed about the architecture, but at a high level, think the 3 panes with the images are the things to focus on. It's meant to be very good for today's simulation and modeling, but at the exascale. Very good for large-scale data analytics, and also very good for machine learning and deep learning. So in addition to being exascale, it's also intended to be able to cover new kinds of applications. And so here's a preliminary list of the many applications that we expect that system to be able to handle. Now, co-design is the way that we're addressing how to build the ecosystem. The applications have to figure out what their needs are, their needs in terms of computational patterns, support software, libraries, and they convey those needs to the software development people and to the hardware design people. On the other hand, some things in the hardware will certainly not be able to be changed, at least not in this time scale. And so the hardware people have to say, in a sense, applications people and software people, you're going to have to deal with this kind of a node, this kind of a memory hierarchy, at least for those first systems. And so the information is feeding in the other direction. And it's a continuous information cycle. And that means that the people doing applications have to be working very closely with the people developing some of the system software and tools, programming languages, compilers, and so on. So co-design, very active contact sport, and it takes extra effort, but we think it's essential to create an ecosystem. Otherwise, there'll be lots of very good work done, but it won't have as much of an impact on the nation and ultimately on the world. So here's, I'll be going through what the application development, the software technology, and the hardware and integration parts of the project do. The goal, as I've already indicated, is to develop many applications and to help them and to use their information to guide the development of the rest of the ecosystem. So, there are ones in chemistry and materials. One of them, NWChemX, you will have the pleasure to get a lot of information on because Teresa Windus will be speaking right after me about that project. We have a number of other applications that deal with things like plasma physics, design optimization for nuclear reactors, and so on. Science applications, and a lot of data and optimization applications as well. So that's a start. Plus, there are 3 that have to do with the nuclear weapons stockpile studies. Altogether, it's currently 25 applications. Many of them use multiple codes, by the way, so it's many more than that number of major codes. So with that, we have a lot of requirements on the rest of the system. Now, I wanted to give you a feel for how those application teams are working. So first of all, they identified, as part of the selection process, what a high-level goal was. So here I'm going to talk about QMCPAC as just one example project. So they have a goal of scientifically performant, that means you can get real science results out, performance portable, that's pretty ambitious, extensible and maintainable open source Exascale Monte Carlo code. So that's a pretty lofty goal, but it's also pretty general. They're starting out with an existing code in this case. Many of the application teams are starting with an existing code, but some are not. And some that had an existing code decided to start from scratch, as you will see soon. So beyond that lofty goal, QMCPAC has a very detailed, specific challenge problem. So every application had to identify a challenge problem that can't be done now. They think they'll be able to do it when they have Exascale. And so that will be a way of measuring success. And it also really focuses the activities. It's not just saying we'll do better science, but in this case, you can see it's pretty specific. Calculate the cohesive energy of a 10,024 atom nickel oxide supercell to an accuracy of 10 MeV per nickel oxide formula unit using a full LCF class leadership computing facility class machine, and also a time constraint in about 1 day. So, and another feature of almost all of these teams is that they're fairly large and they're multidisciplinary to be able to address all the issues, and they're at different locations. In this case, 4 national laboratories and several industry partners. So that's how those, in essence, almost all of those 25 application teams are working. Now, in addition to them, there are certainly some methods such as particle and cell, adaptive mesh refinement, graph analytics that many of the applications need. So we call those co-design centers. So there are 5 of them currently, and they're developing methods and implementing them in software, working very closely with the applications teams as appropriate, as well as working with the software technology folks. Now, for software, of course, the goal is to build a software stack for Exascale that will meet the needs of many applications, not only those 25. And as you might imagine, we have things like programming models, and runtime is a big deal. There are many of them already. Maybe we need to develop some new ones that will be better suited for the new applications or for the new architectures. And so we're working on those, but there are many things associated with it, while at the same time evolving things like MPI and OpenMP so that they will still be usable and underline many of the programming activities. Tools, you always need tools. You need to be able to measure the performance, and that's going to be quite a stretch because of the huge parallelism and the complexity of the individual nodes as well. So tools are another important area. Math libraries are, of course, essential, and we are working again very closely with the applications because we want to make sure that they both serve the needs of the applications and they get adopted early enough to be useful. Data and visualization, no surprise. And then almost as important is how do we make sure that those different pieces can talk to each other, that the software components integrate with each other and with what the vendors provide, and how do we deliver it in a way that's useful. So just being able to integrate hierarchically all those products and to be able to have a delivery mechanism and work with the facilities to have an effective ecosystem. One of the methods that I'll point out here in this a little bit busy slide that shows all the software activities is to think of working with the vendors to incorporate some of our results into their software stack. Now, that's not new. It's been done over and over again, but we're certainly focusing on that. And then there's a new player in town, which is the Open HPC effort. That's part of the Linux Foundation now. And we're going to explore using OpenHPC also as a distribution mechanism. And perhaps that will be an additional, very useful way to do it. Now, the hardware and integration part of the project is now the third of the major technical activities. And it consists of funding vendors to do better hardware for our needs, as well as working very closely with the facilities that will be installing the first systems and making sure that we are producing something that they can install, want to install, and we work together with them to get the applications early access to the systems as soon as possible so that we can be confident that they will be productive almost right away. The hardware R&D is done through a formal RFP process to computer companies because we wanted computer companies to develop better systems that would be products that we can buy and any of you can buy if you find them attractive, as opposed to creating a prototype research in a lab somewhere. So we did the RFP, gosh, it's been quite a while now, and contracts were signed almost a year ago in some cases. 6 companies were chosen, and I think you recognize the names. Of course, they're all here: AMD, Cray, Intel, IBM, Hewlett-Packard Enterprise, and NVIDIA. And our hope is that the work that they're doing will result in better building blocks or better system designs, interconnects, memory hierarchies. That's what they're working on. And that those better ideas are implemented in products so that when people go out for a tender to get an Exascale system in a couple of years, some of those results will be part of a product. Not just a demonstration, but a commercial product. The human resources are as important a part of the ecosystem as any, and so we are also working pretty actively on training and productivity aids. The application teams are all using software engineering practices. In some cases it's new to them, but we want the developed software to be upgradable, modifiable, sustainable, and so that's also important. But of course there are challenges. Some we've talked about for so long you're probably sick of hearing about them, right? The massive parallelism, the memory and storage challenges, reliability, and the energy consumption. So let me dive down a little bit deeper. So applications, for example, well, exploiting the unknown memory and compute hierarchies. As you know, the current nodes are pretty complex and their memory hierarchies are pretty complex, and they're going to be even more complex. So that's a pretty big challenge. It's being met. I think it will be met, but it really requires a lot of effort. Programming models, many application teams are not sure which programming model or models, often plural, they should use. And then using some of the motif-based community software such as what the co-design centers are producing, getting good performance is always a challenge, and performance is enough of a challenge, but how about portable performance? That's even more of a challenge. Many of the complex applications are multi-physics or multi-component, and so being able to couple those is also quite a challenge even today. And we want to give useful information to vendors so that they design hardware and software that will work for our applications. But doing that is complex as well. It's difficult to have proxy applications that are manageable enough and display the right properties. And also we have a lot of applications, a lot of potential proxy applications, and a vendor can't realistically deal with, say, 50 to 70 of them. The concurrency for software is, of course, an issue. Which programming models do we continue developing? Which new ones do we enhance and make sure that they're production ready? Coupling applications that have physics, multi-physics, multiple scales, need to do in situ data analytics and so on. And of course, looking at the future, what will the future applications need that we don't know about enough right now. And now on the other hand, we have a problem that is a good one, in that some of the software development teams in the Exascale computing project have so many application teams working closely with them and wanting to, that they don't have enough people to do that justice. But that's a good problem to have. The applications are engaging with the support software teams. And to me, perhaps the biggest challenge is creating the ecosystem that I've talked about. Having system software that hopefully to the user doesn't look that different on different platforms. Being able to use the software building blocks for applications so that not everyone has to do every aspect of the application, and having compatible APIs, a software stack that can be used from the laptop to the Exascale. And part of the ecosystem is the people. And so we hope there'll be a lot more people who are interested in this type of work, and we have training programs to help with that. The thing to keep in mind is an old saying that I borrowed from a statement many years ago. All aspects of a particular supercomputing system, be they hardware, software, algorithms, or people, must be strong for the ecosystem to function effectively. And so that's a big challenge. And to our mind, co-design is the way to meet that challenge. And it's a contact sport. It requires a lot of effort, a lot of meetings, a lot of phone and video conferences, and even software. We use a software product called Confluence that now has nearly 900 participants, and we can see what each other is doing, their intermediate products, their internal discussions, their milestones, their progress, and that helps. And so there are signs of success. The cost is a lot of people time, but after doing this for now almost 2 years, because we had the first annual meeting in January of 2016, and there were 450 people, and many people going there thought this is a waste of time, but fortunately most of that meeting was not lectures, but it was individual meetings, 15 concurrent meetings of teams getting together and figuring out what they need from each other and how they can work with each other. So it is working. So I'll finish with a few highlights, and I apologize to any teams whose highlights are not presented, because we have over 60 software projects, we have 25 application projects, and unfortunately the SC17 folks wouldn't let me have 2 hours. I don't understand it, but that's how terrible of them. So, and these are a bit of eye charts, but I wanted to give you a feel for the types of things that are already going on. Now, in many cases, we already have software releases. So here, for the Exascale, this is a cosmology application that deals with literally several trillions elements in some of their calculations. So you might imagine they're worried about data and data analysis and so on. So they've released code of 2 of their big simulation codes to the project. So code releases are a big step in every case. They've developed a simulation model monitoring tool to be able to monitor how the simulation is progressing and make decisions. And they're looking at how to use burst buffers for better I/O performance, because they have so much data to deal with. Several years ago, just the hack code in 2 weeks produced 6 petabytes of data, and this was useful data. The ExaWind project, which does the wind turbine farm simulations, was trying to figure out, would higher order discretizations work better on modern architectures? And the little lines in red show that their experimentations so far indicate, yes, higher order methods would be better, and that's important because then it guides their development from now on. The small modular reactor simulation was able to do already the first ever full core simulation on GPUs, developed a GPU version of a transport code, and also improved their cache and vectorization usage. The combustion application implemented software that allows simulation of complex geometries. And that's important because the goal is to be able to have very good simulations of real internal combustion engines with all its geometries. So being able to do that is a big step forward. In the Candle project for precision cancer treatments, they developed a a multitask deep learning network for information extraction from clinical pathology records. And that's important because a lot of the project is going to try to take what are now, I believe, 70 million pathology records and use that information and the treatments for those cancers that were, and their outcomes, and then using deep learning to figure out what treatment for a given individual with a particular cancer and that individual's DNA. Training activities, this is just a sampling of the many webinars, intermediate Git, for people who are not yet familiar with how to handle those repositories, algorithms for modeling, and so on. In one of the co-design centers on adaptive mesh refinement, and this, I must admit, is one of my favorite highlights, because we worry, are we investing in things like co-design centers and software technology, and then the applications will ignore them? But hey, here already 5 of the application teams have said, we're going to use the AMRX software. And so that gives them great leverage. They'll have excellent methods, and they're working closely with those teams. And there's a release of the code. So that co-design center is certainly getting traction. There's another co-design center on discretization of partial differential equations, and you can see they're getting traction from a number of applications as well. So, the co-design, the ecosystem is evolving, so I think we're making very good progress. For the climate model, cloud resolving climate model, obviously that's one example of multi-physics, multi-scale, and so one of their achievements is to integrate multi-scale modeling framework into the ESM data code base software tree, and integrating a cloud resolving model into it, because cloud resolving is essential to that particular project. In a different one, the exobiome project, this is a demonstration of an algorithm that gets much better results scientifically than any existing results. So it's not only able to scale, perform well, but it's even now being able to get better results for that. And then the final one is the QMCPAC example that I used earlier. They, remember, had the goals of performance portability, software integration, worrying about data I/O, and here are things that they've been experimenting with and are starting to make headway in things like performance portability and using tools from other parts of the project. Now in software, it's a little bit more complicated, so I'm going to breeze through these a little bit faster, but I mentioned there are over 60 software projects and they've completed over 200 milestones. Now remember, this is a project, so these activities have milestones. But in summary, many releases of software, some are internal releases, but quite a few are external. So there's progress being made that way. Some of the releases added functionality, things that they couldn't do before. Some had to do with demonstrating integration, interoperability among different components. Of course, performance improvements and improved algorithms. So for programming models in runtime, there's a plethora of examples of things that have been done. For example, release of the verification validation suite for OpenMP 4.5. It's highly useful. Releasing a performance suite for Raja, which is a new approach. Developing Fortran interoperability with Cocos and also the FLang compiler for Fortran. Yes, Fortran is still a substantial part of our software activity, so it's important to be able to keep that going into the Exascale. And sorry, that's on this slide. Toolkit support for various things, demonstrating support for performance instrumentation in the Candle cancer study, and a lot of performance improvements for different kinds of linear algebra and other kinds of calculations. and software releases, you know, a new release of PETC, of Super LU, and Strumpack, all of which are widely used applications and building blocks. In the I/O area, you know, again, many code releases. HDF5, very widely used as part of the project as well. Data warehouse is a relatively new effort, and that's also making good progress. And data and visualization, for example, integrating a new volume rendering capability into Visit, which is a very widely used piece of graphics software, into VTKM as well, which is a building block library for that, and releasing various parts of software. And the operating systems, you know, jitter is an issue. It's certainly going to be a big issue with billion-way parallelism, so characterizing it is important. And you know, integrating you know, a resource manager into the Argo project are some examples. And then I've already given you examples of integration, and here are some more. Because if we just do things separately, they won't magically be able to integrate. So having a concerted effort on integration is important, and it's making progress. Okay, so now you basically know as much about the Exascale computing project as I do. You know, it's supported by 2 U.S. Department of Energy organizations, the Office of Science and the National Nuclear Security Administration. It's part of the NSCI. There are over 800 researchers currently working in the project. And you know, we're driving forward, you know, pre-exascale science and building an ecosystem. Acknowledgement to our sponsor. And again, we are accelerating the development of a capable exascale computing ecosystem. I hope I've given you evidence that progress is being made and reminded you why it matters. Thank you very much.
First of all, on behalf of the committee, I'd like to apologize to all the ECP software and application projects for not having given Paul enough time to highlight all of your accomplishments. Let's see. So we have time for a couple questions before we move on to our next speaker. Anybody? I don't see anyone getting up, so here we go.
Good morning. My name is Anwar Sairan, and I'm the chair of the BRACE Consortium in Europe, Partnership for Advanced Computing in Europe. I would like to congratulate you with this approach for the Exascale, and also to mention the fact that we in Europe, we are also working on an Exascale project, also for similar goals, so keeping leadership in HPC in certain areas, and also supporting the industrial competitiveness in Europe. What I would like to talk about is that in order to reach an ecosystem, you were talking about an ecosystem, it is very important, in my opinion, to look at collaboration, not only on continental level, but also between the continents, because as you mentioned, expertise is very important and scarce. So in certain areas that you were mentioning, of course, we cannot collaborate in all areas. Some areas are sensitive. In certain areas, we do have differences of expertise, and we may learn from each other, also collaborate with each other. So the question that I have, does putting America first form a barrier for collaboration in certain areas which help improve the world and also help improve your own business case?
Thank you for bringing up that topic. In most of my career, I have very often worked with international colleagues. And although in the Exascale computing project we don't have any formal collaborations, many of us in the project frequently attend and participate in workshops in Europe. We invite people from other countries and world regions to some of our activities. But you're right that there is no formal involvement from outside the United States in the Exascale computing project. If I were king, there would be, but I'm not yet. So there are impediments. The political, symbolism. As you use the phrase "America first." So there is information exchange. There is some collaboration, but it is informal. I agree with you completely that working together we're stronger, and that there's lots of great expertise in Europe in applications as well as software. Jesus Labarta, after all, just got the Ken Kennedy Prize. He's from Barcelona, so it's an issue. The way we're doing it is informally, and we do interact with people from Europe and Japan and China.
Thank you.
I wish we could do more.
Okay, thanks again, Paul.
Yeah.